Thank you for joining us today, and welcome on behalf of the Space Generation Advisory Council, a project group on space and cybersecurity. This is our fourth webinar. The other three one can find on YouTube. SGAC is a volunteer organization for space enthusiasts between 18 and 35 years old. Our project group is focusing on cybersecurity issues related to space. If you wish to join us as an advisor or to start a partnership with our group, you may contact Thea or Antonia, the team leaders, and you can find their contact details on our webpage. So if you Google SGAC Space and Cybersecurity, you can find our webpage. Among other things, we exchange information and knowledge via a Slack group, and we interact with experts in the field, which leads us to write papers for conferences, organize webinars such as this one, and who knows, we might have more things planned for the future. Please allow me to welcome my co-organizer, Niels Maurer.
Yeah, thank you, Jim. Just also, hello everybody and welcome to this fourth webinar. I am very looking forward to the two great experts that we're going to hear today, and I hope you have a great time and a great learning experience.
So Niels and myself, we will moderate this webinar. Myself, I work at DLR, the German Aerospace Center. So indirectly, and Niels as well, and this is why indirectly this webinar is sponsored by DLR. That's a bit of a joke. I'm a product assurance manager responsible for ground segment, space, cyber, and data security at DLR Raumfahrtmanagement, in other words, the space administration.
Yeah, and on my part, yeah, absolutely. In my part, so we have the administration side on one hand, and I'm also working at the German Aerospace Center, but on the topic of cybersecurity, on securing digital aeronautical data links. So for me, just a small step from aeronautical industry to space industry. And as such, I'm a cybersecurity expert from the German Aerospace Center on that side.
So today we warmly welcome two fantastic speakers. We will start off with Mr. Howard Weiss, who is the Technical Director for Parsons Incorporated in Columbia, Maryland. Mr. Weiss has worked exclusively on information security problems during his 45-year career in both government service and in the private sector. Mr. Weiss has worked on multi-level secure operating system research and many network security problems for both the global internet as well as other networks. Working on space networking, he was one of the originators of delay-tolerant networking, DTN, and under NASA sponsorship, Mr. Weiss chairs the Consultative Committee for Space Data Systems, in other words, CCSDS, the Security Working Group, and he will talk about that today. There, he helps introduce security concepts, services, mechanisms, and protocols for civilian space missions. Mr. Weiss is also co-chair the CCSDS Space Data Link Security Working Group, which has developed a standard security protocol at the link layer, which integrates with existing CCSDS link layers, such as telemetry, telecommand, and advanced orbiting system protocols. Mr. Weiss holds a BSEE from the Polytechnic Institute of New York, now the New York University Tandem School of Engineering, and an MSCS from the Johns Hopkins University. The second speaker is Brandon Bailey. Would you like to introduce him, Niels?
I would like you to do the honors, please.
Okay. Brandon Bailey is a cybersecurity senior project leader at the Aerospace Corporation. He has more than 14 years of experience supporting the intelligence and civil space arena. Bailey's specialties include vulnerability assessments, penetration testing for space systems, to include industrial control systems, and infusing secure coding principles within the software supply chain. Before joining aerospace, Bailey worked for NASA, where he was responsible for building and maintaining a software testing and research laboratory to include a robust cybersecurity range, as well as spearheading innovative cybersecurity assessments of ground infrastructure that supports NASA's mission operations. While at NASA, Bailey was honored with several group and individual awards, including NASA's Exceptional Service Medal for his landmark cybersecurity work, NASA's Early Career Achievement Award, and NASA Agency Honor Awards for Information Assurance Cybersecurity. He has also contributed to teams who have received honorable mention in the 2012 and 2016 NASA Software of the Year competition. Bailey graduated summa cum laude with a bachelor's degree in electrical engineering from West Virginia University and currently holds multiple certifications in the cybersecurity field. Before we hand over to our first speaker, please let me remind you that this webinar will be recorded and will be made available on YouTube. I kindly ask you to mute your microphone and not share your webcam feeds until we get to your questions at the end of the webinar. Please post your questions during the presentations in the chat area so we can review and select them. Thank you very much. And now I turn to our first speaker, Mr. Weiss. Please go ahead. The floor is yours.
Thank you, Jim. You bring up the first slide. Okay, there we go. Next slide. All right, let me talk to you a little bit about what the Consultative Committee for Space Data Systems is all about and the kinds of work that we do. I've been involved with CCSDS for, I guess, well over 25 years as a result of my working for the Jet Propulsion Laboratory and other government agencies, and partially with NASA headquarters and several of the NASA centers. And it was thought back then that, well, security, well, we don't really need security. But the goal of CCSDS was interoperability. And that was, you know, the thing that everybody was interested in doing. The intent there was we had multiple space agencies. Everybody was kind of doing their own thing. We had two big, large, if you want to call them behemoths, in the sense of NASA and the European Space Agency. And there was this, I guess, the light bulb went off and said, gee, you know, we're both doing the same thing. We're all doing the same thing. Why don't we get together and why don't we develop standards in this arena? Sort of the age-old granddaddy standard that was developed was telemetry, and everybody heard back in the early days of space, you know, they were always talking about telemetry, the telemetry feed, you know, telemetry, and of course, you know, that's a downlink that's coming down from the spacecraft, and we had to have the analogous protocol that was telecommand, and those were where the impetus was. That's where the need to develop standards was that was the basis of the standards growth. Since 1982, when CCSDS was founded, the scope has been expanded, and so there are lots of different things that are part of the overall work area that CCSDS works on. So there's communications, and there's data systems, and there's architecture, and security, and exchange formats, and XML, and things of that nature. So lots of different things, and like that cartoon at the bottom that says we're just not packet telemetry anymore. So there's lots of other things that happen within CCSDS. Next slide. CCSDS, it's an international organization. So there are 11 member agencies, and you see on the right-hand side, the little graphic there, the member agencies are the ones in bold. And then we have observer agencies, 32 observer agencies. Those are the ones on the right-hand side of that oval. 28 nations are represented by all of the memberships. We also have industrial associates. There are liaisons that are affiliated with CCSDS, as well as individual companies. So in terms of the member agencies, the prime shakers and movers of the organization, we have OSI from Italy, and CNES from France, and CNSA from China, CSA from Canada, DLR, our sponsors of this webinar, from Germany, the European Space Agency, which includes other agencies kind of blended in underneath it, including DLR, Roscosmos from Russia, INPE from Brazil, JAXA from Japan, NASA from the US, and the UK Space Agency from the UK. In addition, we have, well, I should say, before I go on to the ISO world, we have spring and fall meetings. We meet we try to meet face-to-face twice a year. This year wasn't so good. This year we had to skip both our spring and our fall meetings. We had virtual meetings, but typically we meet in the spring and we meet in the fall. In the spring, we meet somewhere in North America, and in the fall, we meet somewhere at one of the other member agencies, typically in Europe. This year, we were supposed to meet in the spring in Huntsville, Alabama, which is the site of NASA, the Marshall Space Flight Center. And in the fall, we were supposed to meet at CNES in Toulouse. Like I said, in both cases, we met virtually. And we really, really do hope that next spring we can meet in, actually, we're just going to push everything into 2021. And so we hope in 2021 that we will meet in Huntsville and in Toulouse. CCSDS also is an ISO subcommittee. So the standards that are developed within CCSDS actually move up into international standards within ISO. We're part of TC20, Technical Committee 20, Subcommittee 13, which is the Space Data and Information Transfer Systems Group, and that represents 20 nations. So we are an entity unto ourselves in terms of developing international space standards, but in addition, we move into the ISO world and we become international standards as well. Thank you. Next, thank you for the next slide. This is the overview of the makeup of CCSDS. There are 6 areas, if you want to call them areas. If you want to think of them, 6 areas of work, which are major overarching areas. And then in those areas, underneath those areas, we have 23 working groups. And you can see in this cartoon, there are a bunch of interrelated areas, including spacecraft onboard interfaces, space link services, cross-support services, space internet networking services, mission operations, and then systems engineering is kind of this overarching thing that kind of encompasses all the other areas. So we kind of have our fingers in all the other areas. And you can see by the names of the working groups underneath each of those areas, there's a lot of motion, a lot of things going on in a lot of different areas. Next. And here's how the structure of CCSDS, what the structure of the CCSDS is. As I said, down at the bottom there, we have the engineering steering group, which are the area directors of each of the individual areas, as we just had on the previous cartoon. There is a management council that's the liaisons of the agencies that essentially manage and control the work that goes on within the working groups. CCSDS has a secretariat, which is actually, I didn't update that, I'm sorry. It's not AIAA anymore. It's actually now a different company. But nevertheless, there is a CCS secretariat and an assigned numbering authority. Both of those actually are working under a NASA contract, so NASA actually physically pays for that. And then above that, we have the ISO, as I mentioned before. There are infrastructure providers, liaison stakeholders, mission programs. So in fact, there's an interagency operations group that feeds into CCSDS requirements, higher level requirements, and things of that nature to kind of fill out the areas of work. Next. We publish books. That's what the CCSDS does. We publish various color books, and the colors are just simply a way for us internally to understand what the books really bring forth to the public. Blue books are of the heart and soul. Those are the standards. Those are the ones that are normative, and they move up into ISO, and they're published as international standards. And then you can see the other colors. Magenta, we don't have that many, but those are basically normative, recommended practices. So these are things that we don't necessarily think we need to go through all of the procedures that have to be played out to create a blue book, like testing. We may just write the book, not do the testing, and then just let people adopt it as they see fit. We have informative documents, loads of informative documents, green books as we call them. These are not normative books, but they're foundational. They provide all of the background material. They provide pictures, diagrams, how the protocol is to be used, or how the guidance is to be provided. Along those lines is what we have there. Red books are draft standards. We have a lot of draft standards, things as they move through the working groups. We'll have multiple sets of red books until we agree on, we come to consensus and agree on a standard. Orange are experimental, so things that we don't necessarily want to standardize at this point. We think they may be too immature, and therefore we'll publish them as orange books. Yellow books are administrative. In addition to proceedings and procedures, there may be test reports, there may be guides for the use of, in fact, we have one, there's a guide that Brandon wrote that you'll hear about, that you might hear about, about cloud computing and how we can do testing in the cloud. And then we have silver books that are historical, things that we had in years past that we no longer need or have been superseded, and we've kept them along as historical documents. And then we have revisions. Pink sheets are just revisions of the existing documents. So we may, in fact, not put out a new version of a blue book. We may just come up with errata sheets, as pink sheets, as we call them, as changes to the blue books. Next. And here's just another pictorial of from the CCSDS website. Here's where you can see and actually gather all of the books, all the publications. Unlike ISO, a little plug, unlike ISO, CCSDS does not charge for any of their documents. They're all free, they're open to the public. You can download PDFs. They're all there for the public's consumption, shall we say. And they're sorted by color, they're sorted by area. Next. This is the makeup of the actual working groups, the areas and their working groups. And if you go to the next slide, you can see that there are two working groups actually under two different areas that are concerned with security. There's the security working group, I chair that, and that's under the systems engineering area. There's another group called Space Data Link Security Working Group, or SDLS, and that one is chaired by Gilles Maury from CNES. I co-chair that one, and that's under the Space Link Services area. The reason that they're in two different locations is we saw a specific need in terms of Space Link security. The experts on Space Link were in the Space Link area, and we decided to jointly create a new working group. And so we have a blend of security people and a blend of Space Link people working in that area. And it's been a very successful endeavor. Next. All right, to go a little bit of background in terms of security and the involvement of security in CCSDS. I can remember my first meeting when I attended CCSDS, I think it was in the fall of 1990 something or other, and I gave a briefing on security and why security was important. And the response I got was, well, we do science missions, so we don't need any security. That's for the military people and other, but for science missions, we don't need anything. Well, thankfully that has changed over the years, and everybody's now recognizing that security is a very important piece of any space mission. So we had begun to do security work. It was the mid to the late 90s, I guess it was. We had an ad hoc committee that was concerned with security, and the initial offering was a green book. Basically, this is security for dummies, I guess is the best way I could put it, because at that time there were very few people involved with CCSDS, very few mission planners who understood what went into the integration of security into their systems. So we were chartered to develop guidance, standards, and to consult with other working groups. So essentially, we were the security guys, and we're here to help you. A lot of other working groups have taken us up on that, and we have worked with many others to include and to integrate security into their protocols. One thing that we instigated as part of the security working group is that in the previous, in the era when, well, we don't need security, they just didn't pay any attention to security. Now all the standards track documents must contain a security section, and so they have to have paid it. If it's not real detailed, sometimes they do, sometimes they don't, sometimes they're not sure what they need to put into there, but at least they pay some attention to the fact that there are security issues, there are security requirements, and they have to pay attention to that. Within the security working group, we do have a wide agency membership. As you can see, the logos across the bottom of that slide. So we have membership across the wide spectrum of agencies. Some more involved than others. I could sort of say that there are a core group, and there are some others that either just participate via the mailing list and may not show up to meetings. Some are more involved in the development of documents. Some may just edit or may provide comments. So there's a wide variety of involvement, but we do have a large set of agencies that are involved. Next. All right, one of the things that we have in terms of the two different groups is we have, as I said before, we have Space Data Link Security, and we also have the Security Working Group. So in Space Data Link, we talk a little bit about what the reasoning was for creating that working group and what we do in that working group. The intent there was to come up with a standardized link layer protocol. So we had existing link layer protocols within CCSDS, the all-encompassing, age-old telemetry, telecommand. There was a bidirectional protocol called Advanced Orbiting Systems, AOS, and there's a brand new one that's just getting published now, or just got published now, called the Unified Space Link Protocol, USLP. The problem was there was no way to integrate security into those, or there was no existing manner to do security, at least in a standardized manner. People had done security in the various link layer protocols, but it was all one-offs. They did their own thing, nothing was standardized. So the recognition was that, gee, we should come up with a standardized way of doing it for all of these protocols, and therefore it would be interoperable and it would be cheap because we'd be able to buy it off the shelf. People would actually build those products. We don't have to redevelop it every time. So what we did is we pulled in the subject matter expertise from both the Space Data Link area and the security area, and we have this dual charted group charted by both the Space Data Link area and the systems engineering area. And we've come up with a core protocol and extended procedures that have been implemented and are working successfully. Next. So here's some of the details. There's the book number. It's CCSDS 355. The core protocol it provides mechanisms for confidentiality, integrity, authentication, and anti-reply. It uses mechanisms that look like internet security type mechanisms. We even have a notion of a security association, an SA. So if you look at the protocol, it sort of looks familiar if you're familiar with internet protocols, and that was by design that we did it that way, that we included the kinds of things that we knew people understood. We have also developed an extended procedures standard, which is 355.1, and we realize that there are more things that are needed other than just the core protocol. So that document includes key management and a security association management, monitoring control, and then the structures needed to operate the protocol over a space link. So that kind of completes the loop in the sense of, okay, we had pieces that people could implement but maybe not operate with, and so the extended procedures now allows people to understand and expand upon how that actually works. There is also in development there was a green book created for the core protocol. There is a green book rationale document being done now for the extended procedures that's in process right now, and so that would provide all the background and all the information that would be necessary for somebody to understand it more fuller than just by looking at the shall statements and the specifications in the actual recommendation, in the Blue Book recommendation. Next. All right, here's a pictorial look at where we see the layers. So if you look at the OSI layers, and CCSDS is not a pure OSI layering system because things were actually before OSI layering was published. So we're close, but not exactly the same. And you see off to the right where SDLS kind of fits in the layering structure. So we are essentially a security shim, if you want to call it something, that fits within the data link protocol sublayer. And so it kind of fits between the synchronization encoding sublayer and the data link sublayer. Next. Okay, and here's how SDLS fits function within telecommand, and it sort of lives as a peripheral off to the side, if you will. You have the main telecommand protocol. There are no changes required to TC per se, other than you have to have hooks to call the security, and otherwise nothing changes within the internals of telecommand itself. So the data gets pushed out essentially to security mechanisms and then is retrieved back and then irradiated. Okay, next. Here's the list of security documents that have been published, including their colors. I guess that yellow one may be a little difficult to see at the bottom. We have a series of blue books, which are the standards. We have a set of magenta books, a set of green books, or the rationale, the informative books, and then a yellow book at the bottom, which is the cloud computing testing that in fact Brandon, who will speak next, worked on and developed for us. In terms of the blue books, you see those are all published. They're available on the website. You can download those and use them, read them. Magenta books are the ones that are, well, at this point we had a glossary. We had a security glossary that was a green book, which meant it was non-normative. It was just informative. We decided to make it a magenta book so that any document could use it as a normative reference. So therefore, it held as meaningful within the document. The architecture is relatively old. It needs to be revised. However, within the systems engineering area, there are other architecture projects underway. We are held off on the revision of the space security architecture, specifically because we're waiting for the overall CCSDS architecture work to be revised, and then we will revise essentially in accordance with what the other architecture work does. And then coming soon, we have a key management. In fact, it's done. it needs to go through the final Secretariat processing, and then we should be done with that. You can see from the green books, lots of different rationale, I guess is the best way I can put it, or guidance books. Everything from the first one is the application of CCSDS protocols, the security systems. That was sort of the original Security for Dummies book that I talked about earlier. We have a threat book that is, in fact, there's a revision of that one underway at the moment. It's completed. It also has to go through the Secretariat final processing. We have an update to the encryption algorithm book. We have a guide for secure system interconnection, key management concepts, guide for mission planners. So there's a wide variety of documents that are specifically pointed at for the space community. Next. A little bit of what these books include. The Cryptographic Algorithms book includes a encryption algorithm and authentication algorithms. In terms of encryption, it's AES 256. So there's a single standard encryption algorithm. We recommend counter mode. We also suggest, and again, because of consensus, this was not mandatory, but if you have the requirement to do authenticated encryption, which is highly recommended, then you use AES in GCM mode. For authentication, we have several different algorithms specified. It kind of hurt to do that in terms of interoperability, but there was such a wide variety of requirements that we decided, okay, we're going to effectively create an algorithm. We're going to standardize on an algorithm per each of the I guess I'm not losing the word, but essentially each of the kinds of ways of doing authentication. So hash-based, cipher-based, and digital signature. So we have all three. We have standards for all three, and they may be revised in the future. But right now, those are we're standardized on HMAC, on CMAC, and on RSA. Although we do say that others may be used if the mission planner, or the accreditation agent decides that others can be used. Next. We also have a document. We have adopted IPsec as our network layer security protocol. Rather than develop something new, if a spacecraft is going to use internet type of protocols, they may in fact want to use IP. They may in fact want to use TCP if it's with closer than lunar distances. So we adapted IPsec with an adaptation profile. And what this does is essentially says, whereas IPsec has a lot of options and lots of different ways of doing things, this minimizes those options and only allows the use of the encapsulating security protocol, or ESP. which was the authentication protocol, is not allowed within CCSDS. Next. And here's just actually this is the page right out of the blue book that talks about the supported protocols and how they're implemented within IPsec for use with CCSDS. Next. We still have a lot of work to be accomplished. There are future programs, both in the security working group and in the SDLS working group. So we're looking at other areas like symmetric key management, security threats revision, as I just said, that we're working on. The algorithms document we may revise, that we're revising the green book, we may revise the blue book. We have issued pink sheets for the blue book to increase the excuse me, the key sizes. We have something called the Intergovernmental Cloud-Based Certification Authority, which we're projecting to be either a magenta or maybe blue. And network layer security for space packets, and secure software engineering for space missions. So a bunch of new things that are on our plate for the to be worked on for the future. On space data link, we have, as I said, we're working on the extended procedures green book. It should be done in relatively short amount of time. Next. All right, summary. Security is near and dear to CCSDS and its member agencies. The days of old that security was only for infrastructure or military missions is no more. Everybody needs it. Everybody should be using it. Everybody should be incorporating it. Mission planners have always pushed back because it costs them money, it costs them time, but it's something that's well worth it. They need it. And then one final plug: organizations that are interested in joining CCSDS or have the expertise to contribute should become engaged. And that is from a liaison perspective, that is from university affiliates, that's from various perspectives. It is a free organization. You do not pay membership dues. We do have many people from universities that are contributing or at least commenting on things, and so we invite you to check out the website and join us. And I think that's my last slide.
Well, thank you very much for this very interesting insight into the formal standards and the work you do. As I work in the aerospace region, so I know the works that ICAO does and all the hard effort that goes into standardization, how hard it is to bring all those things together. I can only imagine how hard it must be putting everything for the space domain together. So thank you very much for this excellent overview. Yeah, now we come to our second speaker, and he was already introduced. So I give you Brandon Bailey, and at the fourth workshop of the SGAC, he will talk about defending the spacecraft in the cyber domain. As I understand it, you would like to click through the slides yourself, right?
Yep.
Perfect. So the floor is all yours.
All right. Thank you so much. Thanks, Howie. So I've worked with Howie for a few years within CCSDS, and some of the things that he spoke about on the protocol and the security aspects, we won't dive into that too much, but those are at the protocol level. Information is extremely important in the overall security approach. So we're going to talk about a bunch of different things right now, but I'm getting a little bit of feedback on the caller. Somebody mute the guy on the phone. So if you're interested in this topic, you can refer to a couple of papers that have been published, one in 2019 and one last month. That's a little more detailed than what you see here in this presentation. So what are we going to talk about? Is we're going to kind of introduce the problem as I see it from a security perspective. How we kind of pre-shadowed a little bit of this. Maybe we don't need security like on civil space, although like in the military world, they believe you've always needed it. So it just depends on what background you're coming from. Then we'll get into a little bit of the basics in just command and telemetry terminology. And then we will talk about some open source reporting, high-level cyber attack vectors, and then some gaps and some examples of these gaps, and then we'll get into some protection. So this information is going to be a little dense. There's going to be a lot of the words on the slides, and that is by design, actually. So That way, these charts can be leveraged in future for referencing. But I'm going to highlight the important things per chart. So I'm not going to read the slides to you, but we'll go there. So let me see if I can figure out how
Sorry, Brendan, just people that are dialing in, can you please?
There we go. I muted them all. Sorry, that was you. I muted you as well, but I muted everyone for now. So yeah, so we'll jump right into this material. Apologies for that little bit of feedback we're getting there. So from an introduction perspective, just traditionally, there's been a lot of misunderstanding as it relates to cybersecurity for space systems. So there's varying information out there on like how vulnerable space technology is, spacecraft, ground systems, and things like that. But space systems, the way space systems are defined in this discussion that we're going to have is the ground system and the space system combined. So if you hear me say space system, that's what I'm referring to. I'm referring to ground and space. And these space systems are subject to malicious insiders, external threats, and supply chain threats, just like any other system is. And the cyber threats for space are moving at a pretty rapid pace for the market. So like in the space world, technology does evolve rather slowly, but threats evolve rather quickly. So it's an interesting interrelationship we have with cybersecurity and space systems, because we want to make sure we fly technology that's proven and is robust and resilient, but it may not be resilient to the latest attack vectors that come out. So in my opinion, we must secure the vehicle in addition to the ground system. The vehicle isn't always thought of in that manner, but it is, a computer like anything else. And the important way to do that, in my mind, is defense in depth throughout the entire space environment, particularly the space vehicle. So that's the important part. So from speaking a little bit, I know this is an international call, but speaking from the U.S. side of the house, the federal government, from the IT perspective and kind of generalized cybersecurity, they've structured around the National Institute of Standards and Technology, NIST, the Risk Management Framework and the Cybersecurity Framework, RMF and CFA. And those kind of been the standardizing body, if you will, from an IT security perspective for the federal government. And in other parts of the world, I mean, ISO, I think, is adopted, which they have interrelationship on the security principle side of what they look for. But this, not all this, the NIST documents and standards and principles and requirements and guidelines, not all of those are really translatable directly to spacecraft. It's pretty well translatable to ground systems, but not so much on the spacecraft. There's a subset. By my calculation, I did an estimate and ran through NIST 800-53 Rev 4. And I think I found maybe 25 or 30% of those controls and enhancements applicable to the spacecraft, roughly. Now, on the national security side in America, there is this document called the Space Overlay from CNSSI 1253 Appendix F. You can Google that and it'll show up. And it's an attempt at taking the control baselines and trying to overlay what it means to a spacecraft or a launch vehicle, and it does an okay job with trying to figure that out, but it's still very generic. It's kind of trying to take what exists out there and seeing what possibly could be applicable. And since you don't have mission specificity at this point, it is kind of hard to develop this overlay. So what we're going to talk about is more in line with mission specific baseline development for cyber requirements is some of the stuff we're going to talk about. The Missile Defense Agency also published something for software assurance, but those are the two things that I've seen that kind of relate to translating what's already out there from a regulatory compliance standard perspective on the federal level to space systems. There is a white paper currently developed by NIST on how to apply cybersecurity considerations for satellite technology, specifically small sats on the commercial side, but that's still yet to be published. So while efforts have been made to mold these, uniformity is lacking in guidelines, and there's likely more things that need to be done specifically for space. And through my research of the past year or two, reading all sorts of information and documents, articles on cybersecurity for space, there's a lot of people who definitely talk about how space and cyber, how it's important and we need to be doing better. But there's not a whole lot specifically talking about what are the mitigation techniques and what do we really need to worry about specifically for the spacecraft. That's an area. So in lieu of that, that's where these two documents that have been published on aerospace.org over the last 2 years, 2019 in concert with CyberSat 2019, and then 2020 the Value of Space Summit with Space ISAC and Aerospace put out. Those papers were published, so you can go give those a read for some additional context to the information you're going to hear today. So from a traditional perspective, like I said, there is kind of misunderstanding and complacency about cyber vulnerabilities, and if there are any security controls applied to the space system, it usually is focused on the ground system. And if there are any security mechanisms put on the vehicle, it's really geared around TT&C security. And TT&C security is obviously important. That's how you command the vehicle and get your data down. But there are other threats and things we need to worry about. And so the spacecraft, was perceived to be immune to attacks by traditional thinking, based on a lot of different assumptions. Some of the assumptions were that spacecraft architectures use unique hardware and software that's not susceptible to common malware. Well, if you've heard of Stuxnet, which was that was a particular malware strand that was crafted for a particular instance. So there's others out there, but that is an example of where an adversary would create structured malware for a particular piece of architecture. So it doesn't have to be if you have an adversary going after you directly, it's not going to necessarily be have to apply to a large hardware and software baseline. A lot of times people think that ground infrastructure and how you do command and control is air gapped from the commercial internet. That's not always true, especially more in the civil space arena, and it's getting more and more unlikely as the small sat community explodes and commercialization of space happens. A lot of these command and control infrastructures are going to be connected to the internet, and that's going to bring in some more attack surface. Physical access to spacecraft once launched is highly unlikely. That is true, although there are documented cases of of proximities, spacecrafts getting close to other spacecraft type of thing. So that's getting more and more less of true statement. It's physical access can be possible, and at least on the government side, the thought was, well, our spacecraft are developed by these specialized contractors that have these secured facilities, these secure supply chains, and we use encryption and that type of thing. Well, case in point, supply chains are a hot topic, as we just saw that came out over the weekend with the SolarWinds attack, compromising the software supply chain. So supply chains are a big concern moving forward, and that's applicable to the space industry just as it is standard IT environments. So let's kind of get down to some basics of terminology when we're talking about space, because we may get into a few of these here and there. So I wanted to display this chart so we kind of get on the same page as it relates to what are we talking about when we talk about a satellite? What is the most simplistic form of a satellite system or a space system that we could kind of come up with? And this was just a very generic cartoon diagram to do that. So you have some sort of computing device that's your command and control that interacts with some sort of front end processor that builds out your transfer frames and builds out the packet structure needed to communicate to the vehicle, and then it goes through some modulation process and gets sent to the vehicle. So some of the key areas from a cyber perspective, is the ground system software, is the front end processor, the cryptography units if they have those. Potentially, if you're in other networks, cross domains or like DMZ interfaces, the RF link, the industrial control systems and operational technology that manage all these different components or these facilities, the space vehicle itself. So from a cyber perspective, there's basically anywhere there's hardware or software, that's a cyber threat vector, honestly. So that's just something to be aware of. And when you kind of click to the next one, you see this little animation, just kind of how this translates. I mean, the user would issue some sort of, pseudo command, like turn the heater on or fire a thruster. And then the software changes it into, the right framing and turns it into, binary data that gets translated to serial data that gets turned into RF and sent wirelessly to the spacecraft. So that's kind of what we're dealing with when we talk about space systems in general. So there's the ground component, and then there's the space component that we need to worry about. So just getting ourselves kind of on the same page there. And for those who are questioning why it's a hot topic now with cybersecurity and space systems. For the first time that I'm aware of, a somewhat comprehensive report was put out by the Defense Intelligence Agency that's available open source that talks about, adversary capability as it relates to cyber and security for space systems. So, China and Russia are actively building capabilities to go after assets from a cyber perspective. And there's a lot of different challenges that we have to deal with, in the space sector. And the fact that our mission and acquisition life cycles are so long, and space and the on-orbit time is oftentimes for years and years and years, the threats will always evolve. So your cyber defense capabilities, your cyber protections need to be kind of agile and be able to detect these things. So, we're talking about, some of the stuff we'll talk about is more like protecting systems that are being developed today and in the future. But there's a big component of the space infrastructure that is, in my mind, world critical infrastructure that's legacy. And how do we protect the legacy systems? But it's not impossible. And some of the things that we'll talk about from a protection standpoint, these are things you'd want to build in your systems. But if you're doing like a risk assessment of an already built system, you could leverage some of these things that we're going to talk about to assess, do you have those protections or not, and can you apply any mitigating controls to thwart certain threats. So updating those protections on orbiting assets, would have to be carefully planned and executed. Obviously, enhancing the security on the ground is easier, and sometimes updating on-orbit assets is a little bit riskier than the cyber risk itself. So you kind of got to figure out where you're at in that space. So, those are some of the things that decision makers will have to do when you're worrying about cybersecurity for on-orbit assets that are currently, in space. So from a cartoon diagram perspective, I think this is a pretty good representation of the threat vector and landscape from a cybersecurity perspective. So you obviously have your own ground system that can be attacked. You have the user community that may have a connection to your ground system attacked, and the red lines indicate, as the key says, the red lines indicate what the adversary's avenue, and the green indicate normal communication. In addition to the ground system attack from the user side, you have insider threat. You have maybe some attacks on the industrial control systems or operational technology that controls the ground systems, controls the antennas, or controls the facilities that does the commanding. And then you get into your spaceborne attacks. So these would be, affecting crosslinks, hardware-based Trojans or software-based Trojans on board the asset, or satellite communication through some sort of space-based external attack. And then you have the potential for adversaries that have their own ground system that may want to communicate with your device. So that's where encryption would be extremely important, and some sort of ComSec and TransSec type of capability to understand how to prevent other ground stations that have information about your asset to communicate to it. So keep this picture in your mind for future slides, because we're going to kind of talk about this cyber threat vector graphic in context of adversaries and what tiered adversaries would be needed to attack these type of things. So just keep this picture in your mind, and we'll reference it in a little bit. So given the cyber threat vectors that we know about, given all this information that we've talked about thus far, what are some of the gaps currently from a cyber perspective that's kind of we've seen? So from a ground perspective, and I'm not going to read all these are more for future reference, but to highlight a few is insiders. That's kind of applicable to both ground and space, and it's a really difficult problem, the insider threat. But it is a threat that needs mitigated for sure. Some of the things that to highlight here would be the computer network defense incident response, within the mission operations environment, with the command and control environment, isn't where it really needs to be. And network design and segmentation really lacks where it should be for the most part, as well as software security and industrial control system security. So these are some areas where there's substantial gaps currently, based on experience of working with ground systems for probably 5 years or more. On the spacecraft side, like I said before, TransSec, ComSec, and encryption are the controls, if there are any. You may see some tempest control, but there are gaps on the spacecraft side. That outside of those is the ground system is a vector. Given the gaps that we have in the ground systems, they're obviously in a vector that can affect the spacecraft. The software on the vehicle and the software supply chain, that can be vulnerable to injection. So the design of the software and how it operates, as well as how it's developed. And with spacecraft and the high autonomy that it has, software, years ago, software wasn't doing as much critical action as it is today. And now there's a lot of autonomy built in the spacecraft, and a lot of it's built with software. So software resiliency and availability is key, and you need to have robust testing program and robust development program to really ensure that the spacecraft software does what it's supposed to do. As one other item here would be, there currently is a lack of onboard monitoring, logging, and alerting capability. So it's probably overstated to state it this way, but like a SIEM, like an onboard SIEM, or a defensive cyber operations capability on board the vehicle. So those will be things that need to be kind of researched and put on board. Is with all the autonomy that we're getting on board, and the more and more compute resources that we have on board, there's secure mechanisms that we can develop these onboard monitoring and logging capabilities to alert the potential nefarious actions going on. So these are some of the gaps, and we'll talk about maybe some potential protections going forward. So here's a real life example of a piece of software within the ground architecture that was unsecured by the unsecured design example. So given some of the gaps we've just talked about in the command and data flow that we're talking about, let's talk about the front end processor and the example that we're dealing with. So if we go back to this simple diagram of the command and control with the front end processor, with the modem and the modulation and the uplink. So what we're going to focus on in this example is this front end processor here. This is one of the key components on the ground side for for the communication and the commanding and the telemetry processing. So let's focus on that. That is a high value target, a high value asset in the relation to, from a cyber perspective, in relation to mission operations in this example. So kind of what is a front end processor? It helps with the commanding and the telemetry, and it helps convert all these messages and communicate with the vehicle. We don't need to jump into it. It's just important. Let's just say that. So some of the threats, depending on the mission and how it's architected, there are various configurations for a front end processor, and it seems like all the missions kind of do it a little bit differently. But one of the key items to point out is usually the defenses of the front end processor is really expected at the boundary. They haven't been in the past, which is changing. They haven't been really designed to be robust and resilient from a security perspective, but that is changing. You see this with some of the vendors putting out more hardened implementations of these things. But what I've seen in an example, and this is kind of what these examples prove, is the testing of these front end processors that usually are functionality based or requirements based, and they're not tested for security, reliability, resiliency, and those type of things. So there's some mitigations to these threats, like you can just harden them and test them a little bit more. But the area that we want to highlight is the fact that usually these defenses are meant to be at the boundary, which will be apparent when we go over these two examples, and it'll also show that in this case, the testing of the front end processor by the development organization or even the vendor at this point weren't at this point in time wasn't where it needed to be, and that's how we found these two issues that we'll talk about. So in this example, this was happening during a penetration test. So this is why these type of events and penetration tests are important, and testing is important. So if the vendor isn't doing it or the development organization isn't doing it, these third-party assessments of deployed environments is critical. It's kind of the last step to maybe find an issue that could really bite you. So in this example, this front-end processor lacked proper input validation and lack of authentication for this particular thing. So this software in this case, this was just a Linux box under the hood, and the way the software worked, it was essentially it would accept input over like a URL, like a web call, like kind of like an API call or whatever, and you could execute OS level tasks if you knew how to craft the right message. So long story short, we were able to bypass the input validation and the fact that it didn't have any authentication on that interface. You could execute commands, at the application and operating system level, which ultimately gave us access to root that entire box from the unauthenticated website. So that's just an example of why that can get you, and luckily we found that before it was too late. And for people that are not so don't necessarily understand how this may be tied to existing regulation and things like that, these are obviously principled NIST controls that come in. So in this example, this implementation would fail some sort of accreditation if it was evaluated to this standard. Example number 2 during a pen test is, this is more of an insecure design example. And this was just interesting. This is one of those instances where if you read the design documentation, it just basically tells you that we're vulnerable and that's how we designed it. So if you read the documentation, it says, just write the message to the socket and read the reply. In fact, if you're so inclined, you can telnet to the port and enter the message directly. So that right there tells you that the vendor expected this device to be in a highly protected enclave environment where it wouldn't need to be resilient to anything. It was just protected by the boundary. So that's an assumption that's made by that vendor that their product's going to be put in this type of environment, and that's just an unsecured design principle. It's not defense in depth whatsoever. That's just essentially being lazy in implementation and not providing any type of security to that interface. So in this case, once it took a while for the tester to actually figure out how to structure the packets and interact with it over the telnet interface, but ultimately was able to connect and authenticate or connect and get the thing to process commands that we could reconfigure the front-end processor unauthenticated and cause outages or do whatever. So that's another example of how this works, and another example why pen testing is important. So the next, and these are also NIST controls. So another example that I'll point to is actually, I guess, a little bit of self-promotion. This is a presentation that I did at DEF CON 2020 this past year in the Aerospace Village. So this was a example of an experiment showing you how you can circumvent a satellite's control via replay or command link intrusion if you're not using proper authentication or encryption. So if you're just accepting any type of command, if it's right on the right frequency and in the right packet structure, you'll process it. That would lead to some replay attacks and things like that. So this was an example where was able to do a replay and get the flight software to actually respond and process the commands that were replayed, as well as structure a command, a raw command in the right format and get the right bits in the right places and send that to the vehicle and get it to process it and cause an application on board to restart. So these are just 2 examples of how, and this type of thing is getting more popular, and there's more and more discussion around this topic. So obviously, to prevent this type of an attack, you would authenticate and encrypt your link at the data link or session layer to ensure that your system is not vulnerable to these type of attacks. But another example, also related to encryption. So at Black Hat, there was a talk by James Pavur, I think is his name, and this was a really good talk on how he actually leveraged discover vulnerabilities with commercial internet providers. And he was able to extract sensitive information. The data may be encrypted from at the application layer on the ground, but once it got sent up to the space and then got downlinked down, he was able to snoop the data as it gets sent from the relayed satellite in space down to wherever it needs to go on the ground, and pull that data out of using Wireshark basically, and found all sorts of information, personal information, sensitive ship information, and all sorts of things like that. So that's a pretty good talk if you want to go read that. But it was interesting. It just shows that there's, in this instance, this commercial provider of internet was not providing any encryption, and you can basically snoop on anyone's internet traffic that goes across the wire. And he actually notified the FBI for this and got this privacy industry notification that went out. So this just kind of shows how the market's changing. People are researching these areas. It's getting more and more mainstream. Each year at these hacker conferences, you see more and more talks about this type of stuff. I mean, with what was just done at DEF CON this year with Hackasat, these all things are just moving this industry in the right direction, because you're talking about these issues and correcting them as we go. But there's a cycle that's we're going to go in of where the research may lead to vulnerabilities that we're not aware of and can't fix easily. So I'm not sure where we're going to be in that cycle, but people are looking into this and it's getting more mainstream. So how do we protect ourselves from this? So how do you protect the ground system? How do you protect the spacecraft? Well, the stance that we like to promote within our cybersecurity subdivision at Aerospace Corporation is defense in depth, and that's what the two papers were written in the last 2 years really promote these type of principles, defense in depth. And from a graphical representation, defense in depth can be represented as an onion. And there's a pretty interesting little cartoon here at the bottom, just kind of describing what this means in the traditional sense of an IT onion, from the inner layer to the outer layer. So what we have is developed these onions for the ground system and the spacecraft. So from a ground system perspective, this is kind of the onion representation, from the data that's on the ground to the software that processes it to the endpoint or host that the software runs on, to the network that interconnects all these things, to the border protection and computer network defense and incident response. All this ties together. So you see each layer, there's a menu of options of security controls that you would apply at each layer. And not note, this diagram, you can't fit every subcategory or every security control within the little box. It's it's listed only partially by intent. You can't list them all, but some of the important ones are listed here. Similarly to the ground, we have one for the spacecraft as well, which has the data on board with the spacecraft software with the single board computer, or sometimes referred to as the onboard computer, OBC or SBC. Or maybe it's sometimes referred to as the bus, wrapped around hopefully some sort of intrusion detection prevention, which may or may not be being implemented at this point. But then you have the cryptography, the comms link, the ground system, which shows up in this stack, as well as your prevention system. So if you kind of see how this visually is represented, it shows you, okay, I have a menu of options where I should potentially promote and add security controls. So something to note is the red boxes there's current gaps in almost every area. The physical area within the ground is probably one area where we guard gates and guns. We've got that pretty well figured out for the most part. And then in the comms and crypto area, we got that pretty much figured out for the most part on the spacecraft. But what I would note is there are documented cyber threats or cyber vulnerabilities that exist at each layer of this stack. So that's the importance, is understanding that there are cyber threats at every layer, and depending on what your risk tolerance is, you may need to mitigate ones at every layer or only certain layers, depending on what you want to do. So that's what we're going to get into a little bit, is how do we figure out which layer we need to apply the most security, and which controls at which layer do we need to really focus on. So this is the visual representation. This is a little bit of an eye chart. It's not necessarily meant for you to read all the data here, but you can go back to reference it. So what this is a visual representation of data that was extracted from open source resources, talking about different cyber threats and vulnerabilities as it relates to the space system. And you see that there's kind of certain threats at each layer or vulnerabilities that you need to worry about at each one, and then you kind of go from there. So you will notice here the ground has only got one individual entry. That's because ground in itself, which we'll get into a little bit later, is exploded into hundreds, if not thousands, of specific threats that can happen to a ground system. So, but for the visualization purposes of this diagram, it's just all encompassed in one. So this is just kind of how it looks, and we'll come back to this as it relates to this conversation in a moment. So how do we determine which controls are important? How do we determine which layer we need to apply security and which controls within each layer? Well, it's simple, right? It's not simple, but it's simple in theory, right? Risk management. Risk, that's what everyone talks about, right? Understanding the risk, figuring out where your highest risk area is, and applying the controls accordingly. So you should, it's just basic system engineering principles there. Figure out where my threats have the highest likelihood and most impact, and go from there. So how would you do that? Well, in the space context, this is why I wanted to do a callback to this diagram. Is how do we know within our operational environment, if we're a LEO, a GEO, cislunar, deep space, where in our operation environment, like what is the likelihood of an attack? What would be the impact of an attack? And how do we correlate that to what attackers may really do? So in lieu of having a detailed report for your particular mission, not every mission is going to have, or system is going to have, a detailed threat report saying, adversaries are really interested in affecting your mission that measures rainwater in the Amazon. So that you're probably not going to have threat intel that really backs that up. But what you can do is you can kind of gauge this generic threat model to say, okay, what level of tiered adversary would it take to exploit this vulnerability? And that can help you drive the likelihood calculation. So you'll kind of know what the impact is, and we'll get into that on this slide. So you need to evaluate. So all those threats that were in that eye chart a few slides ago, you could evaluate each one of those cyber threats for your specific mission, given your design information, given your context, and you can kind of evaluate, well, what would be the impact if I had a ground system compromise, or I had a crypto key compromise, or what would be the impact if I had a replay attack on my mission, something like that. You kind of know what that impact could be on your mission from your analysis. The likelihood is a little bit different, so that's a little bit tougher, but likelihood can be a three-legged stool if you think about it from the cyber perspective. So there's the adversary capability. So that's where the generic threat model can come in, where you can try to articulate, is it a tier 1 adversary or a tier 4, 5, or 6 adversary that will be needed to do this type of an attack? And then you can do the difficulty to exploit. That takes into account your compensating controls you may have, your design a little bit, that type of thing. So you can kind of gauge, you kind of know what the adversary capabilities probably are, or you can get information from various sources. You can understand the difficulty to exploit based on your design information. What you might not have a good feel for is what is the motivation, and that's the tough one. Is why would anyone go after me? And that goes to Howie's point that he mentioned earlier, is civil space, and traditionally in the past, I was like, well, that's a military issue, and that's not a civil space issue, because no one will actually try to attack our systems. Well, we've seen that is a false narrative at this point. There's documented attacks that have happened across all sorts of space missions, civil and non-civil. So the motivation's tough. So for the context of our conversation, we're just going to talk about the adversary capability to help drive the likelihood, and we'll talk about the difficulty to exploit at a generic level, and not necessarily at a mission. But those are some variables that would need to be adjusted if you were to apply this kind of methodology to your system. So once you have your, once you do this analysis and get your impact and likelihood, you can help start build out your protections and requirements. And just as an aside, from a legacy perspective, existing missions. So given that, that chart a few charts ago with all the threats, you could evaluate your existing mission given those type of threats and kind of figure out where your gaps are and figure out, is there ways to protect those things, or maybe is there things we can monitor a little bit more closely to see if those type of threats can manifest themselves, or if they do manifest themselves in our system. So just keep that in mind, is this isn't just all just future talk. This is, you can apply some of these ideas to current legacy missions as well. So if you go through this process that I'm discussing, you know, the likelihood calculation, the impact calculation for each individual threat and vulnerability that was on that sheet, you kind of get this 5 by 5 that plays out, and you can, you know, build out your risk tolerance and where you want to be from there. So if you were to do this, you know, on a generic scale, so I'll show you how this kind of plays out. So if you were doing this and you come up with your 5 by 5, and you're basically going to have to establish what your baseline risk level is. Is it anything in the red? Is it anything in the red down into like 17 in the yellow? Is it anything in the red and yellow? Is it everything that has to be done? So given your budget, your time constraints, all these different things, you would establish where your baseline would be. Maybe you're a CubeSat mission that's going to be in orbit for 30 to 90 days, and you really only care about things that are, you know, in the upper right quadrant, you know, 25 or 24, that you care about, because the time to attack you is going to be a lot less than if you're in the air for 10 or 15 years. So those are the type of things that go into this calculation and analysis. So once you've done that analysis and you come up with your, you know, generic baseline of where you want to be, this will be an example of, you know, if doing this analysis for just a generic space system, you know, let's just say civil space mission that does some sort of science collection, you know, that's kind of what this notional representation was. Okay, these are the essential things based on that analysis of where I would apply security. So, you know, these items in red are things that I really care about, that I want to apply controls for. And there's another eye chart on the next slide, 24, that takes all those and puts them in kind of a tabular form of essential that need, and you're not something to read these, this is for reference later, but what I did want to highlight is out of these two, we're going to dive into a couple of areas here just for discussion on particular, you know, advances in technology or ideas or discussion points that we can talk about as it relates to the SBC processor bus or intrusion detection and the ground system. So like I said, this isn't for you to read now, it's for you to read later, and you can kind of dive into that data as you see fit. So some example technologies to kind of address those highlighted areas. This is a tie back to what Hallie presented earlier. There was a space data link security software-based cryptography solution that applies cryptography solutions within the data link packet, within the transfer frame. That way, if you don't have bulk encryption like hardware-based encryption, you can leverage this protocol if you support the CCSDS protocols, and you can you know, get a low swap impact, size, weight, and power impact for encryption. It's software-based that, you know, has AES 256 level encryption type of thing. So there is, you know, some data link layer software cryptography that can be leveraged to get you a little bit of protection from a cryptography standpoint. And this could help maybe in the small sat arena if people really want to look into it. So just wanted to throw that out there as, hey, this is a potential area where things have advanced a little bit from a software cryptography perspective within the data link layer, tying back to this, you know, onboard security type. As well as onboard security is this is a sample proof of concept idea on using Xilinx Zinc, you know, processors to do onboard intrusion detection and DCO type of capabilities with like hardware enforced separation onboard, you know, a spacecraft using these, you know, FPGAs. So it provides that separation. So, you know, you've heard some people that feel like if you put onboard monitoring or security type capabilities on board a vehicle, it opens up an attack vector for various things. Well, with this hardware force separation and the way, you know, this has like certain read-only access to certain areas, it provides some assurance that you can, you know, not have a lot of issues with that type of thing. So this is just an example of a prototype that the Aerospace Corporation is working on as it relates to hardware and force separation and doing onboard monitoring and protection on board the vehicle. But one of the key aspects of like onboard monitoring or onboard defensive cyber operations on board a vehicle is it's got to integrate with fault management. So, I mean, spacecraft for years have been doing, fault redundancy and fault management on board. So, cyber threat is just any other hazard or threat that happens on board a vehicle. So existing fault management is key. Integrating with your existing fault management is key. Because you wouldn't want the cyber protections doing something out of band that the fault management structure isn't aware of. So it's a tightly coupled interaction. It's more like just an expansion of the existing fault management capabilities on board. It's kind of the way I like to think about it, because you can do your FMICA analysis from a system engineering perspective and just bring in cyber threats and cyber hazards, just like any other threat or hazard, and work it through your system engineering process and get some good protections that way. Some other principles to kind of talk about on the SBC side is segregation and least principle. You got to make sure you have proper segregation, isolation on processes, isolation, on the domains of how the things work. And there has been some advancement. Well, it's not really advancement, I guess, but it's been known for a while. But like the ARINC 653 type architectures and its partitioning with real-time operating systems provide you some integrity protections and other type of protections of isolation from a process perspective to ensure that if one bad thing happens in one area, it doesn't happen to another. So you get multiple applications, multiple software levels on the same hardware platform. So that's something to think about from a security perspective. It's not necessarily been thought of in my mind as a security protection mechanism, this ARINC 653 type stuff, but it can be leveraged in that space, because it's more from availability and software criticality and things like that, mission criticality. But just as easily, that principle could apply from a security perspective. If you have some sort of application that has a defect or is compromised by some level, it has some level of isolation and protection. So those are just some things to think about, and some advancements that I kind of am aware of in the most recent years that could really help with some of this. So that's it for the spacecraft side. So let's talk about the ground a little bit. So this is also a little bit of an eye chart. So this is a callback to the defense in depth onion diagram earlier of let's expand that and blow that out a little bit. And this is just a graphic, a visual representation of what is meant by each one of those subcategories. And these all translate to existing standards. I mean, you can I have loose mappings to these to ISO standards or NIST standards or whatever. These are all geared around just standard good practices that you would expect on any type of secure platform. So it's not sort of anything new really, but it's just a different way of visually representing this information that people kind of understand how this kind of protects each layer of each one. So I'm not going to dive into each one of these, but just know that you would apply controls at the data layer, the ground software layer, the endpoint layer, as well as network, and then the monitoring and perimeter and physical and prevention. So there's all these different controls, and what you see in the diagram on the top little pictorial, it shows you that the red boxes of how it correlates to that other diagram. But this is just important. Think of this as a menu of options, giving you a risk analysis, just like on the spacecraft that we're talking about from a threat perspective. You would do similar on the ground side and figure out where you can leverage, existing controls, or where you can inherit security from other places, or where you need to add your security in. So there's a lot of different protections that you can do. You're not going to do them all, but you need to do some of these, probably in each layer, honestly, to get you where you need to be. The next chart is just a correlation of some of this information to the today's market and today's cyber environment is really geared around this attack framework that's put out, that's available. It's kind of open sourced to an extent, but it's out there. A lot of people are leveraging it. But what this is the attack framework was cross-referenced to techniques, tactics, procedures that have been leveraged into ground systems from a penetration testing and assessment perspective. So we don't have a lot of good, obviously threat intel, probably the backup, attacks on ground systems, because that information is more than likely protected, where like if actual attacks were going on against ground systems. But we do have some good information based on doing analysis and doing testing of operational ground systems over 3 to 5 year span. And these are the ones that have been leveraged and can should be protected against that. If you were to prioritize things from the attack framework, these right here kind of correlate with those protections on the previous slides. So if you put protections, some of those protections in, some of these TTPs won't be successful. So that's kind of how this ties together, is just trying to articulate and how tie together how some of your standard IT practices that you would typically do on ground, standard IT applies to ground systems, and how this you can kind of pick and choose with with the protections and with some of these TTPs that you want to mitigate against. So the last slide here is I know I went pretty quick on some of these, but my opinion is personally is there has been a lack of critical space system failures from a cyber perspective. There's been plenty of space system failures over the years, but not a lot that is known about that is strictly security related. But so it's really easy to get lackadaisical and be like, well, this is, it hasn't happened in the past, so let's not worry about it in the future. But we're on the brink of something, I personally feel like, and I don't think it's necessarily an option moving forward to ignore it, because space systems, ground and spacecraft, these are all critical for our nation and the world. Worldwide, we have tons of capabilities that's driven by space. The barrier to entry to space is also drastically reduced. I mean, 20 years ago, it was a lot harder to get assets into space and getting knowledge about space, but now it's becoming more mainstream. You can get launch services. You can use AWS for ground infrastructure. You can have a satellite put together that's the size of a loaf of bread. So all these type of things are possible now. So the barrier to entry is way less. It's less of a specialized niche area than it used to be. And the commercialization of space is really going to open the doors to this, in my opinion. One of the things to point out is our critical space infrastructure are in the sustainment phases right now. So, we may not be able to upgrade some of these from an operational perspective. And decision makers, whoever gets paid to make those decisions, needs to accept the risk in either direction. Either I accept that I'm not going to do anything about the cyber risk, or I'm going to try to fix it, and then the risk of breaking something. So there's risk on both sides. But hopefully, people could leverage some of the information within this chart package and be like, okay, where are my gaps? Like, do a quick analysis of which cyber threats apply to me in my mission currently, and then figure out what would be the impact and likelihood of each one, and figure out if I need to mitigate it or not and make that decision. So the intent of this information was to help both existing missions as well as future missions as you're building secure infrastructure. So risk-based defense in depth, in our opinion, is going to be a big part of the solution, and you got to design it in at the beginning. This is the first reference actually to SPD5 so I won't get into that, but in America, they put out a space policy directive to basically secure the space infrastructure and space missions in September, and that's one of the key components of it is risk-based system engineering to figure out which security controls you want to be in there. And my opinion is you got to have the right requirements. They're key, and without them, you run the risk of unsecure design. So that's been a big part of the work that I've focused on over the past year, is trying to translate, and we've done this pretty successfully to this point, is translate all these known cyber threat vectors for the spacecraft and the ground system and translate those into implementable requirements that can secure the mission. So that's been a big focus area for us, so that we're not our contractors and our contracts and our systems have the right requirements, so we can engineer to those requirements. So I feel like using this threat modeling approach, the generic threat model and this matrix and the 5x5 can really help understand your cyber risk. And if you were to do this from just a standard engineering approach, especially for people who are kind of in this game for a while and kind of do cybersecurity for space, there's going to be a lot of overlap. Like some of these things that's going to come out of that 5x5 analysis would be some of the things you're already doing. So like if you were to do, assuming that you didn't have any security by default, and then do that analysis, yeah, your TT&C link is going to be one of your #1 priorities to secure. So that's going to show up. Physical is probably going to show up. If you have sensitive data on board, tempest controls will show up. So those type of things would show up in the analysis, and it's meant to be, because this whole process is meant to be kind of all-encompassing in my mind, to get all the controls that you need for a mission. And last bullet point here is, it is, kind of my opinion, is we've had inadequate cybersecurity requirements and or governance, and that's led to, in the space industry, that's led to some cyber risk in certain areas, specifically around insider threat and supply chain for both the ground and spacecraft. The crypto and comms area is not as secure as everyone thinks it is for every mission. Key management's a big issue for a lot of people. Situational awareness on board the vehicle is not where it needs to be. We don't have a lot of good onboard monitoring, response, and recovery for the spacecraft, and we have some for the ground, I think, now, but not as where it needs to be. And there's still cyber hygiene issues on ground systems that, software, industrial control systems, monitoring, segmentation. So there's a lot of areas where there's improvement. There's improvement being made currently. You can see this with some of the missions and things that I've worked on, but we still have a long way to go, and we really need to get moving on this. But briefings like this and discussions and getting the information out is one of the key things that we need to do. So with that being said, that will conclude my charts. I appreciate your time. My info should be on the front slide. You can contact me with any questions, but now I'll turn it back over to the moderators for Q&A or further discussion. Thank you.
Well, thank you so very much, Brendan, and also Howard, for your excellent contributions to increasing the knowledge and awareness on cybersecurity issues in space. I would like to start off the Q&A, and this time we do it a little bit differently. We've prepared by chatting to the people that have raised questions, and we would like to get the people to switch on their cameras and their microphones and ask the question, and we will of course do that one after the other. We would like to start off with Aaron Weisman. He was the first person to ask questions in the chat, and I think he has a question for Howard. Howard, also, if you can switch back on your camera and your microphone. So, Aaron, if you can unmute yourself, you should have that capability. Yeah.
Yep.
Excellent. So please go ahead and ask your question.
Okay, so my question is kind of a multi-parter here. I've noticed that the ISO standards are part of the FAA commercial spaceflight standards, specifically the TC20 SE14, and it relates more to anything relating to safety, which obviously this can relate to safety. Anything relating to command and control of a spacecraft can. So my question is, do you see that these standards being pulled into legal requirements at some point? And then with that, how do you see the testing for this being handled for jamming and electronic warfare on data stream, similar to what they did this year at the Hack a Satellite activity at DEF CON?
So the first answer about these standards and regulations going to show up in law, is that the question? Was Senator being required? Yeah, these are going to be legal requirements. So I guess when you say legal requirements, I don't know if you're referring to law or legal from the contract perspective. So what I envision seeing happen is a lot of these security standards starting to get pushed into contract language as these things are being developed. And then I think there are going to be policy directives. You saw in the United States with the SPD5 that was released, it's starting to move the narrative a little bit as it relates to security for space. So I think we'll eventually get in that area where there will be legal requirements for security for space systems. But right now there is a little bit of lack of standardization as it relates to that. I mean, if you do work with the government, there's certain legal things that you need to do, but I think with the commercialization that's going to happen and all the commercial services that are going to be provided, I feel like there are going to be legal requirements eventually as it relates to security, and that's some of the things I foresee in the near future happening and coming out of the federal space, at least on the U.S. side. How you have any input on that?
Yeah, I think the only thing I would add is from the perspective of FAA, they have their own way of doing business, and they may adopt, they may not adopt. It's unclear as how that would work.
And then on the EW side, so there was no EW happening at the DEF CON event, but I'm not sure if your question is more geared towards testing in general at these type of events, or just I'm not sure how that relates, but I think there's going to be more stringent requirements levied on missions that get to mitigate jamming and hardware EW type of attacks. I don't know how much on the testing side that's going to happen. I don't know how they're going to verify and validate adherence to those requirements, if it's going to be tested or if it's going to be more of an observation and design. I don't know if that answers the question, Aaron. I hope it does.
There's a concern that one of the NOAA satellites might have been hacked by China. And so that was kind of what I was interested in, was, are we going to start seeing a requirement for that sort of testing being put in place to verify that civilian systems are resilient against that kind of stuff? And I didn't see that in any of the 720.3 G1 testing.
Yeah, I think that the testing, I think it comes down to requirements, and then the testing follows. So if they have the structured requirements in place, then you're going to have eventually have to verify and validate those requirements, that you adhere to those requirements. Now, is it actually going to be testing and testable? I don't know. That's where that governance structure comes in. Is you're either going to have an acquiring agency say, prove it to me that this is not susceptible to EW and jamming attacks, or they're going to say, based on this is observation requirement, based on your design and what you've implemented, we believe you've met this requirement. So I think it comes down to requirements, honestly. That's my 2 cents.
Let me just add my couple of comments. From a CCSDS perspective, testing is only done to ensure that what we have written to document is workable and is not utter nonsense. We do not do any security testing per se in the sense of pen testing of any of that nature. So that would be the question as to how much testing is done in terms of security would be done by the implementing agency, by the implementing commercial entity, whoever is doing the space mission would have to determine what their security requirements are, both from the integration of and the use of CCSDS protocols and from the perspective of how hard they want the system to be.
So it's more of a use at your own risk at this point.
From that perspective, yes. We try from the CCSDS perspective, we try to build in the best mechanisms we possibly can, but we're not doing the implementations that a mission would use. Therefore, we can't really say anything from that perspective. And we're not doing the kind of pen testing that you're talking about. That would be the mission fielder.
Okay, thank you.
All right, so I believe we have a second question coming up from Antonio. So Antonio, if you're here, if you could turn your camera and unmute yourself, please. There you go. I think you unmuted yourself. Yeah, we can hear you. Perfect. There you go.
Okay, perfect. Hi, this is Antonio from Germany. My question is about Corona. So there have been various articles recently alerting that due to Corona crisis, several critical assets, also space assets, ground stations or operations or satellites are more vulnerable. And that because more and more people are working from home. So home office, telearbeit, it's the Corona is revolutionizing the IT world by letting people more and more working from home. So what is your view? This is a question for both speakers. By the way, thanks a lot, Bailey and Howard. Very interesting. So what is your view about this? What are the measures to be taken in the short and long term? I saw also the layers. So you showed many layers out of the standard way how satellite missions are done now. But I think there's a kind of a new layer called working from home, where we need to see about the assets, and then it's not only about small satellites or GPS or telecom satellites, but we have to think also that maybe there are some operator working from home and looking at the health of an astronaut, for example.
Right. So, in my opinion, what you're referring to is more of it kind of does show up in the layers. It's just not so jumps out at you. But what you're talking about is remote access perimeter control mechanism. So what COVID has done is open up those remote access vectors that may have never been there in the past. So that could be true that these systems are more vulnerable because now you can potentially tunnel in from someone's home network by trying to go through the perimeter control of an existing ground station. So, so I would say that it's obviously a case-by-case basis on how that's architected. So it would be how secure is the tunnel and how secure is the VPN connection that you set up to get into the environment to do the monitoring that you're referring to. So I think what COVID has done is it's probably opened up that opportunity of remote access where it typically would have never been possible or strongly discouraged or only in critical outage times or critical debug times. So I would say it's more geared around it's endpoint protection, that's remote access policy and those type of things is what it would be. So I have certain ideas on how I would assure that would be. I mean, there's several tunnels and jump boxes and various implementations that you can do to secure that, but it is like a case-by-case basis. I think maybe going forward, maybe that should be thought of as something going into the design phase of the ground component, is architecting the secure remote access into this environment so that it's not, because by default it was generally just not done, frowned upon, don't do it. But now it's like probably a necessity to think about how this can happen. So it's more in the perimeter control and how you allow interconnection between the home network and your environment. But there are secure mechanisms that do so that really reduces risk in my mind. If you want to go over the list of things, I can walk through several of those, but just as an example, it's host-based integrity protection on which devices come in, only allow certain types of authenticated devices and authenticated individuals in, and encrypt all the traffic that comes in, and have jump boxes so that you have to tunnel into multiple things and authenticate in multiple ways using multi-factor authentication, and then you can hopefully secure that link a little bit better. But that's my opinion on that topic.
Yeah, I agree that it's really the end systems at that point, because whether you have cable or fiber or satellite communications that are making up the backbone of the network, working from home is only exasperated from the perspective of the end system, that in this case is not controlled necessarily by the corporate entity or by the governmental entity. And sometimes you're using your personal machine, those kinds of things. Phishing attacks, it doesn't really matter what happens with the core network. Now you're tunneling into the secured area, but the end system is exposed, and so that's what we have to worry about from that perspective.
Okay, thank you, gentlemen. We have time, I think, for one more question before we wrap up. I mean, it's been a longer session than planned, but the questions are excellent. So let's do one more question and then we'll call it an end. Mr. Claudio, please go ahead.
Hello, good evening. My name is Claudio. I'm a researcher in space law and policy, and thank you very much for your presentations. You presented extensively on the cybersecurity threats, focusing on TT&C. For this reason, could you please refer to the TT&C, and if there is any difference between the large constellation of satellites in low Earth orbit and satellites in MEO or GEO? Also, could you please provide an overview about the cybersecurity challenges for communication with satellites in LEO, in particular for downlink, especially because satellites in LEO are different than the others from other orbits. They are cheaper. They have a shorter lifespan. So could you please make a difference between the LEO and GEO, focusing on telecommunication and also on cybersecurity for TT&C? Thank you very much.
Let me start off in the CCSDS threat document. It's a green book, but nevertheless, it does actually take into account the various orbit types and the threats that are applicable or probable, I should say, against each of those orbit types. It doesn't necessarily talk directly to TT&C, but obviously that's part of the mix. But we do take into account the fact that that there are different aspects from a communications perspective, depending on what kind of orbit they're in. So obviously, LEO, you have short exposure times in the sense that the satellite's coming around very fast, but you can do it with a very small dish as opposed to deep space, where you're interplanetary, for instance, and you've got long exposure potentially, but you need a gigawatt of power and a 30-meter dish or bigger in order to communicate with it. So the attacks are different, the threat vectors are different, the vulnerabilities are different.
Yeah, so how we hit that kind of nail on the head. So it's so given the context of the way I would talk, so I linked in the green book that Howie's talking about for your reference in the chat, and there's a new version coming out any day now, right, Howie, in 2021, hopefully sometime early. I think it's in its last phases of review. So given the context of what I was talking about for TT&C security, so it is in relation to your mission characteristics in my mind. So if you are a short duration mission, there's only certain threats on the TT&C side that you really need to worry about. If you're doing cryptography on that link, then your key management strategy doesn't have to be as robust if it's a short lifespan, because you don't have to worry about rekeying over a 10-year life cycle or something like that. So there's various things. I think it's all kind of the orbit, like Howie said, there is some generic information in that threat book that kind of talks about it, but it's really just power, I guess a power and visibility type of thing of the orbits is, so like from a cyber perspective, it'd be like your attacks, like when you're on the internet, right, your attack surface is constant because you're always on and in visibility to the adversary. Depending on your orbit and where your adversary may be at, you may be only in short duration based on your orbit. LEO, I think you have, I guess, more opportunities and less power, and you can do that with like just things you can buy. Almost, we'll say Radio Shack, but that doesn't exist anymore, I don't think. But so you can buy something off Amazon and communicate with LEO, whereas these other orbits, you're going to have a lot more difficulty communicating with those. So I think it's just more of a timing and power and resource. That's more that tiered adversary thing from my presentation can help is understanding your orbit, like deep space orbit and things like that. That drives down the likelihood of something. That means you're only dealing with probably tier 4, 5, and 6 adversaries at that point, because you got to have the big dish with all the big power and that type of thing. So those are some of the just characteristics that I would say that you just consider, and it's all a threat-driven analysis and based on your orbit characteristics and how often you're doing things and what type of security you have on board on what the risk would be. So that's about the best I can do on that. I'm not a telecom expert Howie knows more about that than I do. Thanks.
Okay, so thank you also for answering all those questions. Yeah, it's time to wrap up. So I would like to thank the two speakers enormously for their generosity in terms of their time and their wisdom that they have shared with us. It was a very big pleasure to communicate with you in the preparation leading to this webinar. And I also would like to thank the team of SGAC that has helped to make this possible. Also, of course, my co-moderator Niels. Thank you so much for your support. And to all the people that have participated and that asked the questions and that are here to learn about this new topic. So thank you very much, and hope to see you in the 5th webinar that will come in next year. And given the time, I would like to wish everybody a Merry Christmas or other festivities and a good start of the new year. Please keep safe and healthy. Bye-bye.